Our topic today is first modular exponentiation, more generally modular arithmetic, and then I'll describe the Diffie-Hellman key exchange protocol. You can view this as some background so you can start working on your homework in case you already don't know about public key crypto and exactly how to use this sort of stuff from Sage. So I'm going to start at the beginnings. Actually, other people are playing around with this, so I will use my own copy. So I'll start with modular arithmetic, which I've certainly mentioned before and we've done some things with. It's kind of just a reminder in case you forgot. So given a positive integer n, you can consider the ring of integers modulo n. That's the numbers 0 up through n minus 1. And you can add and multiply the elements in here. That's why it's called a ring, because you can add and multiply the elements. And the way addition and multiplication works is you just add the numbers, but then you might end up with a number that's not between 0 and n minus 1. And so what you do is you reduce modulo n. That is, you divide by n and take the remainder. For example, consider the ring of integers modulo 12. Here's a list of representative elements of that ring. And if you take 7 and 9 and add them together, you get 16, which is not in there again. But now if you divide 16 by 12 and take the remainder, you get 4. And so that's by definition the result of adding 7 and 9 in the ring of numbers modulo 12. You can also think of this as, it's 9 o'clock and I plan to sleep for 7 hours. What time will I get up? The answer should be 4 a.m. Probably nobody here identifies with that. But that's actually what I often do. So you can also do multiplication. So r of 7 times r of 9. Remember, r of 7 makes the element 7 in the ring r that's defined above. What this will do, it'll multiply 7 and 9 to get 63. And then it will divide 63 by 12 and get the remainder, which is 3. And there it is, 3. Okay, so that's it. That's the ring of integers modulo n. There's one really surprising, subtle thing about the ring of integers modulo n, which is absolutely critical for every single crypto system that we'll talk about, really every public key crypto system that's built on number 3. And that is, skipping down a little, you can compute powers very efficiently. So here's a little kind of like, math contest sounding puzzle. What are the last 3 digits of the number 1, 2, 3, 4, 5, 6, 7, 8, 9 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9? As you'll, I think, learn in one of the homework problems, if you were to literally write that number out, it would be it would have a lot of digits. Okay? So you probably don't want to just write it out and then look at the last 3 digits. But what you can do, if you want to compute the last 3 digits of a number, you can just compute that number modulo 1,000. If you have any number at all and you divide it by 1,000 and take the remainder, the remainder is just the last 3 digits. To convince you of that, I will write any number at all. Dang it. I have to start with a 0. Okay, I've got rid of the 0, and then I will reduce it modulo 1,000. This divides by 1,000 and takes the remainder, and I get 450. Okay, so that's true. So this thing where I wrote mod number 1,000, I don't have to write r of 1,000. In Sage, you can also write mod, something like this. That creates the element 7, but in the ring of numbers modulo 12. That was actually what I skipped above. This looks like your everyday 7, but it's secretly, if you look at its parent, remembers that it's modulo 12. And if you look at it from the point of view of Python, its data type is integer mod, etc. There's a bunch of stuff there. Okay, so here's how you compute 1, 2, 3, 4, 5, 6, 7, 8, 9 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9 modulo 1,000. You first create the number 1, 2, 3, 4, 5, 6, 7, 8, 9 mod 1,000. which is, of course, just equal to 789 mod 1000. And then you raise that to the power that's given over there on the right. And what it will do is it will, actually not sure exactly what it does, but I know what it might do, which is instead of directly computing that number, so one way that you could compute a number to a big power, kind of the obvious way, would be to do the following. Let a be this number, which looks like that, and I'll just write a times a times a times, and just do that this many times. Let's see, a. Of course, it'll take you quite a while to type all those out, and the number of steps as you do it would be 123 million steps. It's a reasonable thing you could do. It would take quite a while, but it would probably finish, and you'd end up with this product. And every time as it computes the product, it takes the product and then reduces it modulo 1000. So for example, you could do a times a. It doesn't get really big. Every single time, it takes 789 times 789, multiplies that all out, and then reduces it modulo 1000. So you get that, and then you take the last 3 digits. You could do that, but it would take a long time. There's a much better way of computing powers modulo a number. And what you do is you take the exponent and you write it in binary. And then what you've done is you've expressed the exponent as a sum of powers of 2. When you write a number in decimal, you're writing a number as a sum of powers of 10 times the corresponding digits. But in binary, the only digits are 0 and 1. So when you write a number in binary, you're just writing it as a sum of powers of 2. And now, I must feel like writing on the board, but there's no marker, so I won't. So I'll just point to this. If you want to compute a to a large power, you write this power in terms of powers of 2, and then you think, geez, a to a sum of powers of 2 is just a product of a's to various powers of 2, right? Because a to the b plus c is a to the b times a to the c. So if you could compute a to a big power of 2 efficiently, then you can compute a to any power efficiently. And it turns out you can compute a to a big power of 2 efficiently by repeatedly squaring it. You can compute a to the power of 2 to the 100 by just computing a squared 100 times. You take a squared, then square that, and square that, and square that, and square that. That's the basic idea behind fast exponentiation. You can raise a number to a large power modulo n by repeatedly squaring that number, and that will raise it to a large power of 2. And every time when you square, you also reduce modulo n. And now, from that basic idea, you can compute a number to a large power of 2, and since you can write any number as a sum of powers of 2, and since exponentiation works by a to the b plus c is a to the b times a to the c, you can compute any number to any large power you want modulo n incredibly efficiently. Okay? So that's why when you do this, it's really, really fast. See? Try it with time it. It's just a few microseconds. So it's very, very fast. And this holds in a lot of generality. And it doesn't matter. This is just mod 1000, so you might not be convinced. But let's make the modulus a lot bigger. I'll make it that. Okay. It's nice and big. Just as fast. Almost just as fast. Slightly slower. But it's extremely fast. So this is a very, very basic fact about algorithms for working with numbers modulo n, which is not obvious. I read somewhere once, and I don't know if I believe it, that Gauss didn't know about this, which seems weird, but I saw it claimed. But in any case, this one fact enables one to come up with all kinds of really cool cryptosystems, as we'll see. And just to summarize it again, if you have a number modulo n, and you want to raise it to a big power, that is something you could do very, very quickly. Okay, so now let me tell you the first application of this idea, and it's by these two people, Diffie and Hellman, and it's something called the Diffie-Hellman key exchange. It's an idea that just uses arithmetic modulo p, where p is a prime number, to solve the following problem, which is an old problem that people have worried an enormous amount about for thousands of years, which is the following. Suppose two people, or maybe two computer programs these days, like your web browser and Amazon's web server or something, want to agree on a shared secret, which they will then maybe use for encrypting messages later. So to make it maybe feel very concrete, what's your name again?
Mac?
Mac?
Yeah.
Okay, Mac and I would like to agree on a shared secret. And we're able to communicate information back and forth. And everyone in the room could see all the information we're communicating back and forth. So the problem is, how can we agree on a shared secret? By a shared secret, I just mean some big number, maybe a 100-digit number, that after we do a sequence of arithmetic operations, we both know that number, and you watched all the information we transmitted back and forth. You don't watch what we do on our computers, you just see what we send back and forth. And you see everything, but you can't, in a reasonable amount of time, figure out what the big number is that we agreed on. You can see how this could be useful. In the olden days, they would shave a slave's head, tattoo the number there, let their hair grow out, and then send the slave off over to see Mac, and then he would shave their head. So that would be a way to communicate a shared secret. And you would see everything, but you wouldn't see that there's like a secret shaved into or tattooed on the head. But nowadays, we can do much, much better, right? So here's how it works. And by the way, when this was introduced, you can look in, yes?
Is that slave thing made up, or?
No. It's real.
You didn't just come up with one.
Nope. You can't make this shit up. By the way, when this thing was introduced, which I'm about to tell you about, which is really, really simple, you can look up the Mass SciNet review of this paper, and the reviewer's like, I am unconvinced. I don't think this, would work, and it's kind of funny. So if you feel initially skeptical about what I'm about to describe, that was literally like an actual published review of this algorithm when it first came out said that. It was very skeptical. GCHQ, which is like the NSA in England, they weren't skeptical because they had come up with it before these guys, but they didn't think of a good way to use it, I guess, so they didn't, they kept it secret until recently. Okay, so here's what you do. So you have two computer programs or whatever, or people, me and Mac, and we want to agree on a shared secret. So here's the protocol, the sequence of steps. So we agree on a prime number p and a number g modulo p. So we just choose some big prime number. Let's say our prime number is, I have an example here, the next prime after 10 to the power of 100. Okay? So you heard us agree on that. We're going to use the next prime after 10 to the 100. He knows that, I know that, you all know that we're going to use that. And our g, we'll just make it 2. So it's not too complicated. So we've done step 1. We've agreed on a prime number p and a number g modulo p. Good? It's a very concrete one. Everybody heard us. They can all write it down and compute it. Now, I'm going to generate a random number a. You can't see the number I'm generating. And then I'm going to compute g to the power of a modulo p and send it to Mac. Everybody can see that. And here's what happens when I do that. So let's go down here. Step 1, we agree on a prime number p and a number g. Everybody sees that. Step 2, I generate a random number and I compute g to the power of a. Because g up here was actually defined to be mod 2 comma p, it remembers that it should always be modulo p. And so when I write g to the power of a right there, it is very fast and so on. So this is what I send. So to Mac, I send the number 896154, etc. Okay? And so everyone sees me sending that. He hears me sending it, and he writes it down. Okay? Now the third step is that he does exactly the same thing. This algorithm, this protocol is extremely nice because it's symmetrical, and that we both do exactly the same thing. It's kind of like the nicest, cleanest, simplest public key crypto system you can possibly imagine. So the next step is Mac generates a random number up to it's less than p, so a number between say 0 and p minus 1. It'd be really stupid if he generated 0, but it's unlikely. And then sends g to the power of b. Okay? And then the number he sends, which for some reason is in here, let me run this step by step. Notice I set the random seed, which is so that it's reproducible. So here's the number that he sends back to me, 705, 307, etc. And again, you guys can see this number as well. You hear everything, you see everything. The one thing that we know that you guys don't know is A and B. I know A, that random number, but nobody else does. And Mac knows B, and nobody else does. I don't even know B. Now here's the trick. We now need to agree on a shared secret. And that's what we do next. I compute the number that Mac sent me raised to the power of my random number A that I generated. That's right here. Okay, and this is what I get. This is something that I do in secret. Nobody sees this. You guys don't get to see this. All you so far what you've seen is that number, this number, and you know what prime we've agreed on and what the base is. But you don't see this, and you can't easily compute this because you don't know what little a is. Only I do. And that's the number I get. Now the miracle here, the miracle of algebra, is that when Mac computes, what Mac does is he takes the number I sent and raises it to the random number he generated. He combines exactly the kind of information he has, and he gets this number. And they're the same. And they're the same because if you take a number and raise it to the power of A, and then raise it to the power of B, you get the same thing as if you take that same number and raise it to the power of B, and then raise it to the power of A. It's just basic algebra. And that's why these two are the same. And we've now agreed on a secret. And now we can use this secret in a range of different ways to communicate information back and forth. And you guys can't decrypt it. So like we could, for example, we could write down a sentence and then shift every letter by, I could shift the first letter by 2 and the second letter by 5. We'd use 10 letters. So shift the first letter by 2, the second letter by 5, etc. And that would allow us to send, we could use this as a one-time pad, for example. Kind of stupid, but there's much better ways to encrypt things after you have this. Yes?
But it always has to be like intrinsically linked to your secret, the way you code things.
Yes. Yep. So we would send them back and forth. We'd send all kinds of things like my bank account number is this, and tomorrow morning we should meet at 7 a.m. and blah blah. And then 5 years later, maybe somehow you actually do figure out what our shared secret is because you have all the information you need to find it. Maybe you just number crunch really hard with some supercomputer, and eventually you do figure out what the shared secret is. If you captured all of our communication, you could then decrypt it. Which is why some people might be interested in capturing a lot of communication, even if they can't decrypt it immediately. Okay, so first let's think about this for a minute. I just claimed, I'm just going to go back up to the overview of what we just did. Here's the overview, or the description of the steps, but without all the code. I'll just go through it really, really quickly. We agree on a prime number and a modulus. We agree on a number g modulo p. I generate a random number and send g to the a, mod b. Mac generates a random number and says g to the p mod, g to the b mod p. I compute the shared secret, which is g to the a to the b. Mac computes the shared secret, which is g to the b to the a. And math ensures that those two are the same. Okay, that's all it is. It's ridiculously simple. If you had to implement this, it wouldn't really be that hard. It's just a little bit of code. It was actually in the 90s that it's illegal to implement this if your prime number was sufficiently large, because it was considered a munition and it was controlled under like military export regulations. I'm not joking. It's completely ridiculous, but true. Public key crypto is strangely restricted. And you'll see people like Hillary Clinton make crazy statements about restricting crypto that don't make any sense if you understand anything about the math of how it works and how simple it is.
I'm curious what she said.
You'll have to look for yourself. People say funny things when they don't understand math. That's what I do. I definitely do when I don't understand some math. Okay, so that's it. So here's one point. If you see everything that we did, you do have enough information to determine the shared secret. It's just hard to do, presumably. So let's suppose you watched all the communication back and forth. You saw all the numbers we wrote down. In particular, I generated a random number A and computed g to the A and set that. You could figure out what my A is by simply computing g squared, g cubed, g to the fourth, g to the fifth. It's going to take a while to get up to A, but eventually you'll get up to A. It might take, more than the life of the universe, but eventually, in theory, you would get up to A, and then you would go, oh, boom, his A must have been that number, because g to the A is that. So you have all the information you need to figure out the shared secret. Everybody who saw your transmission back and forth has all the information you need. It's just that it takes a long time, as far as we know. So there are a bunch of tricks, though, like if p minus 1 is a product of a bunch of small primes, then there's an algorithm to efficiently solve what's called a discrete log problem. The problem, given g to the power of a and g recovering a, it's kind of like computing the logarithm of, remember logs, those funny things that let you solve certain equations? So if you, in calculate, or high school, if you had to solve g to the a, if you had like x equals g to the a, you take logarithms of both sides. And then you take log base g, and then you have log base g of x equals a. So you can, I think I just did that backwards. So you take log base, no, that's exactly right. So you took log base g of this, that would give you a. And so if you could somehow do logarithms mod p, then you could solve, given g, p, and g to the a, you can figure out what a is. Once you know what a is, you can easily figure out the shared secret, just like he did. I mean, just like I did. I knew a, so I was able to figure out what the shared secret is. So, so there are lots and lots of tricks in various cases when p is constructed in some special way, which let you recover a given g to the a mod p. However, if you choose things sufficiently randomly and do a bunch of checks, it appears, as far as we know, that there's no super fast way of solving the discrete log problem. Nonetheless, people put a lot of work into trying. And we'll see more about that in some of the homework problems and so on. Okay, so that is the Diffie-Hellman key exchange. And let me summarize what I meant by some of the attacks. So, so just a little more about this. So this is just summarizing what I said. If you're watching everything we send back and forth, then you know g, p, g to the a, and hence you can determine a. It's just really hard. By the way, there's absolutely no theorem in the sense that mathematicians have theorems. There's no theorem that says it is difficult to compute a given g to the a mod p. So it's an open problem to prove that it's actually hard to solve the discrete log problem. It's basically an article of faith. It's like you make this assumption in cryptography that it's hard to solve that problem, and then based on that assumption, you then say, this is a good crypto system to use. But you don't actually know that that assumption is true. It's extremely difficult to prove that it's difficult to do things. There's this, for example, one of the clay millennium problems is P versus NP, which is a question about proving that certain classes of algorithms are really hard. Or certain classes of problems are really hard computationally. There's one thing. If you can build a really fast, sufficiently sophisticated quantum computer, then you can solve the discrete log problem very quickly. So watch out for people building quantum computers. Okay, so that's one attack. You just solve the discrete log problem. Looking right here, I've written it right here, covered by my stupid tooltip. I've written it as a logarithm. Okay, the second trick is, let's suppose that Mac and I aren't in the same room. So instead of us literally just directly yelling at each other and you see everything we do, instead we write down a message and then we send it off with somebody, and then we write little messages on paper and we send them off and then we get them back and forth. And he's in another room. Okay, that's a much more realistic situation. So what if I think I have this trusted person. I can write something down on a piece of paper. He runs off to Mac. He gives it to Mac. Mac writes something back, and I get it back. It seems fine. But what if that trusted person thinks he's talking to Mac, but he's actually talking to, what's your name again?
Jake.
Jake. He's really talking to Jake. Jake from the NSA. So the guy takes the piece of paper, he runs off to Jake. He says, hey, Mac, here's the piece of paper. And you're like, I'm Mac, thank you. And then you take the piece of paper, and then you send it off to Jake. And then Jake you send him like a different version of the piece of paper. And then Jake gets that piece of paper, and he goes, oh, thanks, William, for that piece of paper. And then he writes something. So basically, it goes back and forth. But every single message that we transmit back and forth goes through Jake of the NSA. If that happens, I think I'm talking to Mac, but I'm really talking to Jake. And Jake thinks he's talking to me, but he's really talking to Mac. And so as that goes back and forth, Jake is the man in the middle. Every message is going through him. But what happens is I set up a secret key, a shared secret, but I'm really doing it with Jake. And Mac sets up a secret shared number, and he does it with Jake. And now we communicate back and forth, but we're using a different secret. And every message I send, I think I'm sending it to Mac, but I really send it to Jake. Jake decrypts it because he knows the secret. He re-encrypts it and then sends it on to Mac, back and forth like this. So maybe the transmission's a little bit slower, but we don't know the difference. We don't know that it's really going through Jake. So that's called a man-in-the-middle attack, and it really does get used by NSA and other people to you? No. Do you use it?
Well, I'm studying cybersecurity. So
Okay, so it really does get used. And what you have to do, there's security certificates, so there are tricks to try to avoid this man-in-the-middle attack, but if you're sufficiently sophisticated, you can avoid those problems as well. So, I mean, Jake can avoid those problems. Because, if he's the NSA, he can just show a little muscle and people will, let him fake the certificate or something. So, that's the second one. And there's another one which will be part of your homework, which happened very recently. Agree on we don't know for sure what happened here, but you agree on a generator G and a prime number P, and you do everything. Except, what if the prime number P is actually composite, and you know the factorization? So literally in a program called SOCAT, which is a network security tool, an engineer at Oracle put in a patch 1 year ago, which made the prime number P composite. And then it got used for a year, and this is one of your homework problems to do some arithmetic with this thing. But somebody might know the factorization of that prime number. It's kind of hard to factor, it's really big. And if they do, then they could probably use that in some way to get a backdoor into all the security involving that tool. So I'm being vague, but you'll see in the homework problem what happened. It was discovered in February this year. So another way is to do something like that. There's all kinds of subtle, tricky ways of getting backdoors into crypto systems when you're generating the parameters.
So the engineer is being stupid or malicious?
We don't know.
Okay.
So you can read about it. People tried to figure out the answer to that, and when the number was put in the code and it was like encoded in big endian and it wasn't prime, but if you re-encoded it in little endian, then it would be prime. But it wouldn't be a good prime to choose. So it's hard to tell whether they're being stupid or what. Okay, so that's everything. You now have 20 minutes to get going on your homework. Maybe I should just show you the homework really quickly to get you going in that direction. So there are 5 problems. The first one is about modular exponentiation. And the main part of the problem is to take the next prime after 10 to the 100, and then the next prime after that. So these are 2 100-digit primes. And raise one to the power of the other, and tell me how many digits it has. Okay? And compare the number of digits of p to the power of q to, say, the number of atoms in the universe. Estimates. Thereof. Okay, the second problem. Hey. Oh. So there's another crypto system that does a bunch of things that Diffie-Hellman doesn't do, called the Rsa Cryptosystem, RSA. That's what we're going to talk about on Wednesday. And instead of choosing a single prime number p and working modulo p, with RSA, you choose a product of two prime numbers, p and q, and you work modulo that product. And if you can factor p times q, then you can break everything you do with the cryptosystem. So in this problem, somebody, I guess, was it Jonathan? I think, yeah, Jonathan made up a product, p times q, but he did it in a sloppy way. He chose a random prime p, and then he chose q to just be the next prime after p or something like that. In other words, p and q are very close. And because of that, it's easy to factor p times q. So this is like a mistake you might make if you're creating a cryptosystem, and you wouldn't realize that it actually makes it really easy to break. So that's what that problem is about. Okay. This problem is similar. If you know, this is about the fact that if you know that an integer is of the form p times q, and you happen to also know Euler phi of that number, then you can find both p and q. If you know an n and phi, then you can factor n. And here's why. You can just use the quadratic formula. You know the coefficients in some quadratic polynomial whose roots are p and q. So it's pretty easy. Here's a crazy thing that is the result of some recent research. So in this Rsa Cryptosystem, which gets used, I mean, there are literally tens of millions of actual running Rsa Cryptosystems. So examples of products p times q, and they're generated using you create a prime number by choosing something at random and then finding maybe the next prime after that random number. And it turns out that if you look at tens of millions of these, because of stupidity in how they're generated, often when you take the GCD of two of them, you find that they have something in common. And if you have two numbers of the form p times q, and they have a non-trivial GCD, two people are in deep trouble, because those two numbers, you've just found one of the factors of the two numbers, and hence you can factor. And so that link is about a project where people have downloaded the keys associated to lots and lots of computers, and have found that a shockingly large percentage of the keys are amenable to some sort of attack where they can actually factor the modulus, just because people aren't choosing their primes p and q sufficiently randomly. Like if I choose a prime p using a random seed of 0, and you choose a prime using that same random seed, you get the same prime. So that's really, really bad. So anyways, that's what this problem's about. Then the last problem is about what I just told you, which was this. There's an actual deployed implementation of Diffie-Hellman in something called SOCAT, which is a security and network monitoring and analysis tool. And there's the prime p. It's written down. It's right there in the code. But it turns out it's not prime. So we're going to look at primality of it and so on. And if you follow some of these links, you can look at the actual Git commits where the code was added by some company named Oracle to this program, and so on. You can look at speculation about why it was put there, and so on. And I think that nobody knows how to factor this number. You can factor off a few small primes, but the actual full factorization isn't known, even though it is factorable. It is like what you do is when you go through this problem, you'll find two small factors, and then you'll find that the result is also composite for sure. You just don't know what its factorization is. Okay, and that's the homework. So start working on the homework, and we'll walk around and help you.